Hello, and welcome to Differential Equations. This is lecture 31, Fourier cosine series. Last time, we talked about how to write a function as a sum of sine functions. This time, we're going to go over more examples of the Sturm-Liouville theorem. Okay, so last time we saw that just like matrices can have complete sets of eigenvectors, sometimes differential operators can have complete sets of eigenfunctions. And then we can expand any sufficiently nice function as an infinite sum, as an infinite linear combination. This is guaranteed by the Sturm-Liouville theorem, which we now recall since we'll be using it. Okay, so for this theorem, we suppose we're given a function p such that it and its derivative, as well as a function q and a function w, are continuous. On the interval AB, and we suppose the functions p and w are positive. Then we consider the weighted eigenvalue problem. L of y is equal to lambda w of x times y for the operator L of y is equal to minus the derivative with respect to x of p of x times the derivative of y with respect to x plus q of x times y on the interval AB, subject to the boundary conditions. Alpha 1 y of a plus alpha 2 y primed of a is equal to 0. Beta 1 y of b plus beta 2 y primed of b equal to 0. Right. Of course, we need that alpha 1 and alpha 2 should not both be 0, and beta 1, beta 2 should not both be 0. But then under those conditions, we can conclude that first, there are infinitely many eigenvalues, call them lambda 1, lambda 2, and so on. All of which are real numbers. And they satisfy that the limit as n goes to infinity of lambda k is plus infinity. The eigenspace of each lambda k consists of multiples of a single function, y sub k. Third, eigenfunctions corresponding to distinct eigenvalues are orthogonal in the following sense. So we replace the dot product with an integral against the weight function. So the integral from a to b of yi of x times yj of x times the weight function dx is equal to 0 if I is different from j. Okay, and then the fourth, it says that any sufficiently nice function can be expressed as a linear combination. So I wanted this time to give you a more precise statement that worked for one of the examples we did last time. So here's a more precise statement. If f and f prime are piecewise continuous on AB, right? So that means that at every point of discontinuity, you have the limit from the left exists and the limit from the right exists. And we define alpha k in the way we saw last time. So you take the product of y of x with f of x multiplied by the weight function and integrate, and you divide that by the integral from a to b of y of k of x multiplied by itself, and then by the weight function dx. Then the series k goes from 1 to infinity of alpha k yk of x converges at every point in the interior of the interval and satisfies. So if you take this sum and what you converge to is 1/2 of the limit as s approaches x from the left of f of s plus the limit as s approaches x from the right of f of s, right? So if this function is not continuous, then what should this limit go to, right? Because you might have a discontinuity like that. So then what should this sum converge to? And it turns out that if you have a jump continuity like that, then it converges to right in the middle, the average of the limits from the sides. Okay, so that's a more precise statement of the convergence part. I didn't want to state it like that the first time around because I wanted you to have a couple of examples under your belt before giving you more precise statement. Okay, let's work out another example. A couple of lectures ago, we found that if you look at the eigenvalue problem, minus y double prime equals lambda y primed of 0 is equal to 0, y primed of L is equal to 0, then the eigenvalues are n times pi over L squared, with n starting at 0, and the eigenspaces are multiples of the function cosine of n pi over L times x. Note that in difference to the Fourier sine series we talked about last time, this includes the eigenvalue 0 with its eigenspace given by just multiples of the constant function 1. Right? Also notice that the Sturm-Liouville theorem applies with p equal to 1, q equal to 0, and w equal to 1. Parts 1 and 2 of the theorem are borne out by our computation of the eigenvalues and eigenfunctions. Right? Because part 1 tells us that there are infinitely many eigenvalues, that they're all real, that they have no finite accumulation points, so they go off to infinity. Part 2 tells us that all of the eigenspaces should be multiples of a single function. Right? So then for part 3, we can pick any function from each eigenspace. So here we'll just take yn to be cosine of n pi over Lx. And then part 3 of the theorem guarantees that if we integrate one of these functions against another one of these functions, we'll get 0 if n is different from m. This is also easy to check directly using the trigonometric identity. It says that the product of two cosines is equal to 1/2 cosine of the difference plus cosine of the sum. Also using this identity, we can compute that the integral from 0 to L of cosine n pi over L x squared is equal, well, let's treat the case n equal to 0 separately. So if n is equal to 0, that's just the constant function 1. And if you integrate that from 0 to L, you get L. And if n is not equal to 0, then we could use this trigonometric identity to get, this is 1/2 of 1 plus cosine 2n pi over L x dx. And this is L over 2, right, which is just what you get by integrating this constant part, because the trigonometric function, you're integrating over a full period, and the cosine over a full period integrates to 0. So that's what we get if n is different from 0. Right, and that computation is useful when it comes to part 4 of the theorem. Part 4 tells us that any sufficiently nice function f defined on the interval 0L can be written as an infinite cosine series. This is known as the Fourier cosine series of f on the interval 0L. We, of course, also have a formula for the coefficients. So first we have the general formula, is the integral of f of x against cosine n pi over L x dx divided by the integral from 0 to L cosine of n pi over L x squared. Right, and so that gives us, well, 1 over L times the integral from 0 to L of f of x dx if n is equal to 0, and 2 over L times the integral from 0 to L of f of x cosine n pi over L x dx if n is not equal to 0. Okay, let's do an example. Suppose we want to find the Fourier cosine series of the function f of x equals x. on the interval 0L. Okay, so to find the series, we just need to compute these coefficients. Let's compute the 0th one separately. Right, so this would be integral from 0 to L of the integral. This would be 1 over L times the integral from 0 to L of x dx. Right, x integrates to x squared over 2. So that would give us 1 over L times L squared over 2. So L over 2. And then for n greater than 0, we have alpha n is 2 over L times the integral from 0 to L of x times cosine of n pi over L x dx. Right, so we're going to integrate this by parts. So we'll take u to be x and dv to be cosine of n pi over L x dx. So if u is equal to x, then du is dx. And if dv is cosine n pi over L x dx, then v is equal to L over n pi times sine of n pi over L x. So we end up with 2 over L times, so u times v, so it's Lx divided by n pi sine of n pi over L x evaluated between 0 and L, then minus the integral 0 to L of v du. So that's L over n pi times sine of n pi over L x dx. Okay, so let's take a look. Sine of n pi over x, if I evaluated L, I get sine of n times pi, which is always 0. And if I evaluated 0, I get sine of 0, which is 0. So this term is just 0. So we're left with this term. So we could pull out the constant, and we have minus 2 over n pi. And then we have the integral of this sine. So it's going to be minus L over n pi times cosine of n pi over L x evaluated between 0 and L. So that's 2L over n pi squared times cosine of n pi minus cosine of 0, which is 1. So that's 2L over n pi squared times cosine of n pi is minus 1 to the n, then minus 1. And so that's equal to 0 if n is even, and minus 4L over 2 over n pi squared if n is odd. Thus, we find that x is equal to L over 2 plus the sum k goes from 0 to infinity of minus 4L divided by 2k plus 1 times pi squared times cosine of 2k plus 1 pi over L times x. Okay. And as we reviewed a moment ago, this sum is guaranteed to converge at every point in the interior of this interval, and it converges to exactly this value at that point. So we've now found expressions for x in the interval 0L that involve only cosines or only sines, it's pretty remarkable that we're able to express x, which isn't trigonometric at all, in either of these ways. Let's define curly C of x to be L over 2 plus sum k goes from 0 to infinity minus 4L over 2k plus 1 times pi squared cosine of 2k plus 1 pi over L x, right? So this is just the right-hand side right? Here, the Fourier cosine series of x. And let's do curly S of x to be 2L over pi times the sum, and goes from 1 to infinity, minus 1 to the n plus 1 over n sine of n pi over L x. Right, so which is the Fourier sine series for x. So we know that on the interval, the open interval 0L, we have x is equal to the cosine series and x is equal to the sine series. What about for x outside this interval? Okay, well, first, let's think about what happens for the x's in between minus L and L. So C of x is an even function, meaning that C of minus x is the same as C of x, while S of x is an odd function, meaning that S of minus x is minus S of x. So that means that if we're looking at the graph of C of x, right, then we know what's going on here between 0 and L. It looks just like x. So because it's an even function, then it's just reflected that way. While S of x, right, because so we know that between 0 and L, it looks like x, but because it's an odd function, for minus, if I change the sign of x, I have to change the sign of y as well, which means that I'm going to end up with something like that. Okay. Next, note that both of these functions are periodic with period 2L, right? So all of the functions involved are periodic with period 2L. The constant, of course, is just constant, so it's periodic with any period you like. So their graphs are as follows. So let's draw. Here's L, here's 2L, here's 3L, here's 4L, minus L, minus 2L, minus 3L, minus 4L. So if we start with this and then we continue it periodically, what's going to happen is we're going to go up, then down, then up, then down, so on. While over here, right, if here's L, here's 2L, here's 3L, 4L, minus L, minus 2L, minus 3L, minus 4L. Then if we repeat this periodically, we're going to get that, 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 like that. Okay. Notice that C prime of x is discontinuous. And S of x itself is discontinuous. But in either case, they are piecewise continuous. Also, notice that over here, at the points of discontinuity, we know from the statement of the theorem that the function actually converges to the midpoint between these endpoints. Okay, so although these two functions coincide with the function x on the interval 0L, that doesn't tell you what they're going to be doing outside of that interval, right? What they do outside of that interval is fixed by the fact that this is an even function, this is an odd function, and then by the periodicity. The function x itself is an odd function, but notice that that doesn't constrain us for the behavior of this cosine series, because we've only decided what it does inside this interval. And so we're free to extend that outside of the interval however we like. And this function extends in this way. Okay, let's work out a different example. A couple of lectures ago, we found that the eigenvalues eigenfunctions of the operator L of y equals minus y double prime plus 2y prime, subject to y prime of 0 equal to 0, y prime of pi equal to 0, were lambda equal to 0 with eigenspace given by arbitrary constant functions, and lambda equal to 1 plus n squared, where n varies between 1, 2, and so on, with the eigenspace of 1 plus n squared given by arbitrary multiples of e to the x times sine of nx minus n cosine nx, be arbitrary. Okay, this is also handled by the Sturm-Liouville theorem. Although we have to do a little bit of work. So first notice that if you multiply L of y by e to the minus x, then that's an integrating factor here. I can rewrite this as minus e to the minus x times y prime prime. So that if you have minus y double prime plus 2y prime equals lambda y, right, like we studied a couple of lectures ago, then you could rewrite this by multiplying both sides by e to the minus 2x as minus e to the minus 2x y prime prime equals lambda e to the minus 2x y. Hence, the Sturm-Liouville theorem applies with the function p given by e to the minus 2x, the function q is again 0, and the weight function is also e to the minus 2x. Okay, so the theorem applies, and like before, we can see that part one of the theorem, that there are infinitely many eigenvalues, they're all real numbers, and they converge to infinity as n goes to infinity. That holds. Part two of the theorem, that every eigenspace is just a multiple of a single function, that also holds. For part three, we can pick one function from each eigenspace. So here, let's take y0 equal to 1 and y sub 1 plus n squared equal to e to the x sine of nx minus n cosine nx. And then part three of the theorem, guarantees that the integral from 0 to pi of yj of x, y, k of x times e to the minus 2x, the x is equal to 0 if j is different from k. Right, again, you could prove that, check that by hand, just doing some integration by parts, but in this case, that would be a bit more involved than in the previous. Part four of the theorem, guarantees that any nice function f on the interval 0 pi can be expanded in an eigenfunction series right? F is the sum of alpha k, yk. Well, maybe I'll write it as alpha 0 plus the sum n goes from 1 to infinity of alpha n y 1 plus n squared with alpha j given by the integral from 0 to pi of yj of x, f of x times e to the minus 2x divided by the integral from 0 to pi of yj of x squared times e to the minus 2x dx. Okay, very good. So feel free to stop watching there. But if you're interested, I'll give you a little historical context by telling you about the Fourier that we keep mentioning. Joseph Fourier, who was alive between 1768 and 1830. Fourier was born the son of a tailor in the village of Auxerre in Bourgogne, France. His mother died when he was 9. His father died the year after that. Thanks to a recommendation by the local bishop, he was educated at the local convent school, and he was a good enough student to be allowed to study in the local military school. His mathematical talents were clear at that military school, and he was offered a teaching position there soon afterwards. Fourier was sympathetic with the ideals of the French Revolution, and he joined the local revolutionary council in Auxerre. He came to regret confronting a rival faction and defending his own faction when he was visiting the city of Orléans, as this led to his arrest in July 1794 by the infamous Committee for Public Safety. Fourier feared that he would go to the guillotine, but fortunately Robespierre got there first, and the Reign of Terror ended. Fourier was released, and a little while later he was selected to study at the new École Normale Supérieure, where he studied under 3 of the most prominent French mathematicians of the time, Laplace, Lagrange, and Monge. Then in 1795, he became a teacher at the prestigious École Polytechnique. In 1798, with Monge and others, Fourier accompanied Napoleon on his expedition to Egypt. He and most of Napoleon's companions were left behind in Egypt after Nelson destroyed Napoleon's fleet, and Napoleon escaped to Paris and carried out the coup of 18 Brumaire. Fourier stayed in Egypt until 1801, engaged in extensive research on Egyptian antiquities, and acted as an administrator as French-style political institutions and administration were set up. While in Cairo, he helped to found the Cairo Institute and was put in charge of collating the scientific and literary discoveries made during the time in Egypt. Fourier returned to France in 1801, and Napoleon appointed him as prefect, so governor basically, of the Department of Isère. He served in Grenoble and organized the draining of swamps and the construction of a highway to Turin. Only the French half of the highway was built, but still it was impressive. He put together an impressive description of Egypt, detailing the research carried out during the French expedition. Napoleon was sufficiently pleased with Fourier's work to make him a baron in 1809. Following Napoleon's fall from power in 1814 and 1815, Fourier was appointed director of the Statistical Bureau of the Seine in Paris. In 1817, he was elected to the Académie des Sciences, And then because of his work in Egyptology, he was also elected to the Académie Française and the Académie de Médecine. He died in 1830 after falling down some stairs in his home in Paris. Fourier worked out the theory of heat flow in 1807 while in Grenoble, so on top of all of his administrative duties, but it wasn't published until 1822. He based his reasoning on Newton's law of cooling, which we've come up against previously. This says that the flow of heat is proportional to the difference in temperature. Using this, he worked out what's now known as the heat equation. Fourier worked on it in 2 dimensions, where it would look like this. The variation of temperature with respect to time is proportional to the Laplacian in space. So in 2 dimensions, just second derivative with respect to the x variables plus second derivative with respect to the y variables. In analyzing this, he made the controversial claim that any function, continuous or discontinuous, could be expanded in what we now call the Fourier sine series. The reception of this claim was mixed, with many prominent mathematicians, including Lagrange, expressing strong skepticism. Fourier was not the first to use this sort of series. For example, Euler had previously derived the Fourier sine series for the function f of x equals x, and Lagrange himself had used trigonometric series. The question of which functions could be expressed this way led to a lot of work, including re-examining the very concept of a function. Another important scientific accomplishment of Fourier is the discovery of what we now call the greenhouse effect. Fourier made some careful computations and decided that solar radiation was not enough on its own to explain the warmth of the Earth. His solution was that the Earth's atmosphere must act as an insulator. The Swedish meteorologist Niels Gustav Ekholm, around 1900, started calling this the greenhouse effect. All right, we'll stop there, pick it up from there next time.